In 4.5, we're going to set up and solve the related rate problems. In the last section, we set them up, but we didn't actually solve them after. Okay, so let's go ahead and start off reading the first one. We're going to draw the picture and label the variable to start with. Okay, so the width of a rectangle is increasing at a rate of 2 centimeters per second, and its length is increasing at a rate of 3 centimeters per second. At what rate is the area of the rectangle increasing when its width is 4 centimeters and its length is 5 centimeters? So let's just start out with what we're doing. There's a rectangle. Okay, it's telling me that the width is increasing and the length is increasing. So I'm going to go ahead and label them W and L. Okay, now what else do they tell me? They want to know at what rate is the area of the rectangle increasing. So this has to do with area. So let me just start out with the area of this particular rectangle is going to be the length times the width. Okay, then I'm going to go ahead and look at the information they gave me and the related rates. Okay, so I drew a picture, I labeled the variables and the constants. I'm writing an equation relating the variables, which is the area equals length times width. I'm going to derive it, but first let me think about this. Okay, they're telling me the width of a rectangle is increasing at a rate of 2 centimeters per second, and the length is increasing at a rate of 3 centimeters per second. So the width is growing as time goes on. The length is also growing at the same time, but at a different rate. So this rectangle is getting bigger on the width and the length, but at different rates. Okay, as they are both growing, it makes sense that the area is also growing at its own rate. That does depend on the rate of change for the width and the length. Okay, now they want me to evaluate it at a specific moment in time when the width is 4 and 5, but really, first thing is I need to see how this rate is growing, and then I'm going to take a snapshot of it at the exact moment it told me to. Okay, so let's do the next step. Let's do the derivative. This is changing with time because this is centimeters per second, so I'm going to do the derivative with respect to time. Okay, so the derivative of A is dA dt. Well, it's 1 times dA dt. Equals for length times width, I'm going to use the product rule. So let's do the length, the first one, times the derivative of W, which is dW dt, plus the width times the derivative of L. Derivative of L is 1 times dL dt because I'm doing the derivative with respect to time. Okay, next it says substitute the known quantities and solve, and then state the answer as a complete sentence. So now I'm going to go back into the equation and see what they gave me now that I have this set up. Okay, the first thing they tell me is the width is increasing at a rate of 2 centimeters per second. So they're telling me that dW dt is 2 centimeters per second. Okay, what else do they tell me? The length is increasing at a rate of 3 centimeters per second. So dL dt is 3 centimeters per second. Okay, at what rate is the area of the rectangle increasing? So they want me to find dA dt at the exact moment when W is 4 and length is 5. Okay, so these are all the values I'm going to substitute in. I want to find dA dt, so that's the unknown quantity. Let me substitute in everything else. Equals, at the exact moment I want to evaluate it, the L is 5. dW dt is 2. The width is 4. And dL dt is the 3. Okay, now that I've substituted everything in, I'm going to evaluate dA dt. So that's 10 plus 12, so that's 22. Okay, let me think about the units because this is a word problem. Okay, so dA dt, this is 22. That's the area over time. The area is going to be centimeters squared per time. In this case, the time is the seconds. So let's answer our question as a complete sentence. So what are they asking? At what rate is the area of the rectangle increasing? Okay, the area of the rectangle is increasing at a rate of 22 centimeters squared per second. Okay, let's go ahead and look at one more example now that we've seen all the steps involved. Okay, this example should look familiar because it's the same one we set up last time. Okay, so a police car is approaching a right-angled intersection from the north, and it's chasing a speeding car that has turned the corner, is now moving straight east. Okay, so if you remember this from yesterday, there's the police car. He's coming from the north. Boom. Okay, the car he is pursuing has already turned the corner and is going to the east. Okay, so this is the car's trajectory over here. This is a right angle right here. And then if you remember from yesterday, we closed this and made it a right triangle. Okay, I'm going to go ahead and label the values they've given me, or the unknowns. Let's call this y. We'll call this x. Let's call this z. I know that the relationship between these variables is x squared plus y squared equals z squared. And then I'm going to go back and read the problem and look for the values that they have told me about. Okay. He's cheating. He's turned the corner and is now moving east. When the police car is 0.6 miles north of the intersection. So police car 0.6 north. So they want me to evaluate this when y is 0.6. The car is 0.8 miles to the east. So the car is 0.8 miles to the east. So x is 0.8. The police determined with a radar gun that the distance between them, between the police car and the car, is increasing at a rate of 20 miles per hour. Okay, so the distance between them is z, which means dz dt is increasing at 20 miles per hour, so it's positive. Okay, the police car is moving at a speed of 60 miles per hour. Okay, let me look at the police car. He's going this way at 60. Okay, since he's going this way towards the corner, the y value is decreasing. So the y is changing in a negative way. So this is actually dy dt equals negative 60. And it's negative because the y is decreasing. It was not indicated in the information because speed is always positive. So we always indicate it as speed. Okay, what are we trying to find? Okay, what is the speed of the car? So we want to find dx dt. All right. Okay, let's find the derivative and then we'll see if we have all the values we need. So I'm going to go ahead and do derive this. This is 2x dx dt, since I'm doing respect to time, 2y dy dt, which is 2z dz dt. Let me plug in everything I know, and then we'll go from there. So 2 times the x I'm evaluating this at is 0.8. Dx dt is 20. No, it's not. I'm trying to find dx dt, so let's keep it dx dt. Plus 2 times the y is 0.6 when I'm evaluating the rate. Dy dt is negative 60. 2 times z. Uh-oh, I don't have z. Okay, let me figure out what z is in a second. Do I have dz dt? Dz dt is 20. Okay, so I do need the z value. Okay, let me look at this equation. Okay, I know that this, at the exact moment I'm evaluating it, this is 0.6, this is 0.8. I need to find z. So now I have to actually use the Pythagorean theorem to find my z value because I need it for the equation. Okay, so 0.6 squared plus 0.8 squared is z squared. Okay, I'm going to put that in the calculator. I get z squared equals 1, so I get z is 1. Or I noticed that that was a 6, 8, 10 triangle. Okay, so now I know that z is 1, so I'm going to go ahead and plug the 1 here. Okay, now let me see what I have now. 1.6 dx dt plus, not plus, minus 2 times 0.6 times negative 60 minus 72 equals 2 times 1 times minus 40. So 1.6 dx dt. I'm going to add this 70. What is that? 112. And then I'm going to go ahead and divide. So I get dx dt is 70. What should be my units? Okay, this is the speed of the car. Speed of the car is in miles per hour. So this is going to be 70 miles per hour. Let me go ahead and state that as a sentence. What was I trying to find? I'm trying to find what is the speed of the car. Okay, so I'm going to just start with the speed of the car is 70 miles per hour.